All right, so today in Precalculus, we're going to talk about Chapter 5, Section 5, properties of logarithms. So we're going to start working with properties of logarithms. So log base a of 1 equals 0. So let's convert that back to exponents to show that this property is true. So if our bases, if we have y equals log base a of 1, then that's a to the y equals 1. And then we say that a is equal to 0, or sorry, y is equal to 0. So this is our base. This is our what we're equal to, it's our answer, and then this is our exponent. So if a to the y equals a to the 0, then y equals 0. So right now I want you to highlight this property with your highlighter. Log base a of 1 is equal to 0. Because really it's saying if I raise anything to the 0 power, it's going to equal 1. So it matches up with that exponent property, where anything to the 0 power is 1. All right, so if we want to show that log base a of a equals 1, we're going to say y equals log base a of a. Convert it back to exponential form. A to the y equals a. So what does y have to equal in order for a to the y to equal a? Has to equal 1, which makes it possible to say log base a of a is equal to 1. It's like saying, what do I raise a to get a out in exponential form? So go ahead and highlight this property here. That is a property we're definitely going to use, or actually, and highlight them both down here. All right. In the properties given next, m and a are positive real numbers. A is not 1. R is any real number. Log base a of m is the exponent to which a must be raised to obtain m. So when you take a log of base a of m and put it in the exponent of the same base, so it's as if I am putting in the exponent of a, you just get out the m. So a to the log base a of m is m. The logarithm to the base a of a raised to a power equals that power. So log base a, and then the opposite is true. If I take log base a of a to the r equals, it equals just the r value. And this may seem crazy, but we are going to use this to solve logarithm equations. It's kind of saying, how do I undo a log? Well, I raise both sides to the a power, whatever my base is in my log, and it will get rid of that log. It's like it undoes the logarithm. And the opposite is true. How do I undo a base a? If I take the log base a of both sides, it undoes that base a, and you can cancel it out. So let me show you how this works. So if I have log base pi of pi to the cubed equals 3, so if you take pi to the 3 and take the log base pi of it, you get out just the 3. If I take log base 5 of root 3 and put it in the exponent of base 5, I just get out the root 3. If I take e to the 0.35t and I take the natural log of it, I just get out, if this is a typo, please not, I just get out 0.35t. All right, now these are the fun ones. So if I have two items inside a logarithm being multiplied, log base a of m times n, it is the same as taking the log base a of m plus the log base a of n. It's the same as taking each individual one and adding them together. The way I remember this is logarithms are the inverse of exponents. What's the exponent rule when I am multiplying the same base? What do we do with the exponents? We add the exponents. So it couples together. So here this is like, oh yeah, I'm multiplying these together, so I add it. It buddies up with the exponent rule. So I don't memorize both sets of rules. I just say that they're the same. Exponents mean if I multiply the bases, I add the exponent. Same here with logarithms. And it's the same when you do quotients. Log base a of m over n is log base a of m minus log base a of n. So when I have division inside my logarithm, do not be fooled. If it's log base a of m over log base a of n, that is not the same thing as what we have here. And then if I have a power inside my logarithm, I am allowed just to go ahead and move it on outside. So if I have this power r inside my log base a of m to the r, I can go ahead and move that r out front. It is one of the most beautiful properties of logarithms. It takes whatever's in the exponent, just move it out front and multiply it by that log. Awesome. All right, so we're going to write a logarithmic expression as a sum or difference of logarithms. So we're going to take properties, log base 2 of x squared times the cubed root of x minus 1 as a sum of logarithms. So we're going to use our properties. So we're going to split these up. I have two items being multiplied here. So I'm going to go ahead and split it up as log base 2 of x squared and log base 2 of cubed root x minus 1. Now I'm going to go ahead and move the exponents out to the front. Well, first we changed the cubed root to a 1/3 power. Remember when we, way back when, in ancient days at the beginning of last semester when we changed roots to fractions. A cubed root is the same as a 1/3 power. And then we're going to bump the 2 and the 1/3 out to the front. And that's as far down as we can reduce using those properties. Okay, we're going to do that again, but we have log base 6 of x to the 4th over x squared plus 3 quantity squared. And we are going to go ahead and use the division rule, where we can write it as the difference of the top, the numerator, minus the difference of the denominator to log base 6. And then we're going to move those exponents out front. And that is all we can do with that. Why can't we use the addition property on x squared plus 3? Why can't we write that as 2 as log base 6 x squared plus log base 6 3? Why can't we use that logarithmic property for that? So we can't use the multiplication property because we don't have multiplication right here. So we are done with this after we take the exponents and put them out front. All right, using natural log, we got x cubed square root of x minus 2 over x plus 1 squared. And we have not only multiplication but division, and we can do both of those. Anything being divided, we can write as a minus the natural log of, so you take natural log of the top minus natural log of the bottom. Then we rewrite our roots as fractional exponents. So we go ahead and pull those exponents out. We rewrite this multiplication as addition. So log of x cubed times x minus 2. We write as log of x cubed plus log of x minus 2 to the 1/2 power. Pull those out, and then this is just a little double check. Make sure I don't have any matching logarithms, because then I would have to, that would be like a like, that would be to me like, that would be a like term. I would have to combine those together. All right. So now, this is what we've been building up to, writing a logarithmic expression as a single logarithm. So we're going to use kind of the reverse of our properties, which I believe is called the converse. So 3 natural log of 2 plus natural log of x squared. So I'm going to go ahead and bump that 3 back onto the 2. Then we're going to use the reverse of our multiplication inside a log property. So we're going to put them back together into a log. So it's 2 to the 3rd times x squared, all inside the natural log. Any questions about that? Yeah, Josh. All right, so for B, I'm going to take my coefficient in front of my logs and stick them back onto the interior. So I have log base A of 4 to the 1/2 and minus log base A of 5 squared. This minus sign means I'm going to put it as one log with division. So 4 to the 1/2 power is 2. It's like square root of 4. And 5 squared is 25. So this gets written as log base A of 2 over 25. All right, now a little bit longer one with C. I'm going to put my coefficients all back onto, well, just for the first 2, back onto the values inside the log. Then where I see addition, I'm going to write as multiplication inside the single log. And where I have a minus, this is going to go in the denominator. So if I have plus, those go in the numerator. Where I have minus, that goes in the denominator. They did it. So this is one more step. They combined the multiplication into one log. And then lastly, 2 cubed is 8, 3 to the negative 2. The negative 2 means bump it down to the denominator to get 3 squared. And this guy, because it's minus, is in the denominator. All right, so if m is equal to n, then when I take the logarithm of both sides, of both items, that is also equal. Or if my logarithm of m is equal to my logarithm of n, then just my m and n are equal. So we're going to use that property to kind of manipulate logarithms and find undefined variables. All right, next learning objective is to evaluate logarithms whose base is neither 10 nor e. So we're going to approximate log base 3 of 12, round our answer to 4 decimal places. So we rewrite it as y equals log base 3 of 12. And you go, that's base 3 of y, so 3 to the y power equals 12. And then I can take the natural log of both sides, because when you take the log of something and it has an exponent, you can go ahead and move that exponent out front. So then all I have to do is divide both sides by natural log of 3. And I get natural log of 12 divided by natural log of 3, and I can plug that into my calculator. That's approximately 2.2619. I would take a moment and try it on your calculator to make sure you know where natural log is, you're typing things incorrectly, and you're getting out 2.2619, because it's better to get that figured out now than when you're trying to take an assessment on it, and your mistake isn't in your knowledge, it's in your ability to use your calculating device. All right, so that is what we did in the last example, the long way to do change of base. So we use change of base when we have things other than base 10 or natural log, because our calculators don't do anything but natural log and base 10 of log base 10. So when we get into that situation, I always remember it as when I have log base a of m, it always goes log of the big over log of the little. So you can change it to whatever base you want, whether that's natural log or base 10 would be the reason we do it, but technically you can change it to any base you want. To change the base, you go log of the big over log of the little. And in order to get an approximate value out of your calculator, we'll usually go log or natural log. Okay, so we're going to approximate log base 5 of 89, and we're going to go log of 89 divided by log of 5, or natural log of 89 divided by natural log of 5. Either way will get you the right answer. And B, we're going to go log base root 2 of root 5. So that's log of root 5 over log of root 2, or approximately 2.3219. And it doesn't matter whether you use natural log or base 10 log. Both of them will get you the same answer. All right, so these are properties. It is going to behoove you to have those memorized. We really didn't use, we'll use this one more in the next section, especially when we're solving logarithms. And that's it for today.